SDRs.
Yeah.
Oh, cool. This is going to be quite a good demo for that then.
You're planning to grab 3 parts of the midterm grade, though, right?
Yeah, I can do that. What parts are left?
Huh?
What parts are left?
Just check on grades, though.
Okay, sounds good.
Before Friday.
Yeah, sure. Yeah, this is kind of the last big thing I have to do this week, so I should be able to.
Yeah.
Mm-hmm. Ooh, this is nice. Never gotten to use the wireless mic before. I feel so professorial. All right. Hello, everybody. Welcome to welcome to your first EE 120 lecture after the midterm. Just kind of to gauge the field a little bit. How's everybody feeling about the midterm? That's good. I had heard some reports that it was a bit long, which, like that. These things can happen sometimes. But we decided to partly make it up a little bit by having this be sort of a chill post-lecture week. I don't know if y'all read the Piazza post about this. Well, actually, I know that about half of you did, I guess, because there are 50 views, thereabouts. But Murat is actually out of town this week, or out of the country properly. Or not all this week, but he's out of town today. I think he'll be back in the next couple of days, because he'll be teaching the Thursday lecture again. But he has entrusted today's lecture, since he's out, he's entrusted it to myself and Professor Mickey Lustig, and we're going to use up this time slot to do some kind of very relaxing, sort of cool signals and systems related stuff that's mostly going to be hardware demos that you're kind of excited about some of the material that we've been learning, right? Because you've done a lot of mathematical analysis for all this kind of material now, so now it's kind of time to reap the rewards for that a little bit, just by sort of, seeing a cool demonstration that you'll understand quite well for all the effort that you put in. So today's lecture is going to be structured in the following way that I have up here, is that I'm going to start off by doing what we've titled Signals and Synthesizers, in which case I'll take you all on a guided tour of what I believe to be a very cool piece of hardware. It's the Moog Werkstatt 01 analog synthesizer, which was put out, I guess, a couple of years ago, 2014 according to this. But it actually has a lot of cool analog circuitry in it that dates all the way back to the 1960s, to the early days of analog synthesizers and the birth of electronic music. So I guess, again, to gauge the field a little bit, does anybody here have an interest in electronic music, or just music in general? who doesn't like music? And electronic music's all right, too, if you're into that kind of thing. So this is actually sort of a callback to a lot of where that kind of started. And it's a pretty interesting tool, I think, for engineers and musicians alike. So to let you all have a bit... Whoop, stuck on something here. To let you all get a little bit of familiarity with it, I actually have a couple of them here. So I'm going to pass this one around so y'all can see sort of what it's like to look at it and sort of see one of these things and sort of get a feel of what this, let me remind you, musical instrument is like. And you can see that it's sort of the kind of thing that's, designed by an engineer, because it kind of looks like the front face of an oscilloscope, if you ask me. But it can do quite a lot of cool things. And I have another one here, and you'll be seeing that in the document cam in a little minute, after I sort of give my spiel. And so we'll be able to, you won't just get to look at it, but you'll get to see me sort of playing around with it and seeing what it can do. And if all of that excites you, then I have some good news that on Friday, Murat and I have collected a whole bunch of these synthesizers. And instead of the usual sort of mini lecture worksheets kind of discussion section on Friday, what we're going to do instead is we're going to have all these laid out in Cori 204. And basically what's going to happen is you can come on down and play around with them and, sort of see for yourself what it's like to use one of these things and to sort of invent and discover new sounds using your signals and systems knowledge. And there'll be sort of some patch sheets and worksheets as well, in case you want some guidance on what to do and what to explore. But if you just want to embark on your own soundscape adventure, you're also free to do that too. So look forward to that on Friday. So part of what today's guided tour is going to be about in the first half of the lecture is going to be kind of getting you ready for that in a way. And after that, Professor Mickey Lustig is going to be coming in, and he's going to be the professor that will be teaching EE 123, which is our DSP class, which is sort of, I guess, sort of a successor to this class where this class is sort of just general signals and systems knowledge. 123 focuses specifically on the discrete time signal processing aspect. It's all about digital signals. And those kind of classes are very cool. It's one of the favorite classes that I took in my undergrad, was the DSP class. So I highly recommend it. But Mickey will do an even better job of convincing you that it's worth taking, because he's going to show off some of his software-defined radios, which is actually a radio that's defined completely, using programs and computers and stuff like that. And I guess all of the labs and demos in 123 use these things. So if you think that part of the demo is cool, I highly recommend giving that class some consideration. So that's what's going to happen today. But before we get to the SDR stuff, we'll have to go through my thing first, which is going to be, like I said, signals and synthesizers. So the way that you would call a piece of equipment like the Werkstatt 01 here would be a modular analog synthesizer. And I've kind of broken down what that means here, because it's sort of some terms that may be foreign, a little bit, foreign to engineers and musicians alike again, but that all have a pretty direct meaning, actually, in terms of your signals and systems knowledge. So we'll start off with the first word, synthesizer. Before going into this class, does anybody have some familiarity with synthesizers, like kind of what they are, what they do? So a little bit, but in case anybody's sort of never heard of this kind of thing before, or it's been a while, basically what it is that it's basically, I like to think of it as, it's a circuit basically, a piece of electronic equipment. It's sort of an instrument, both in the sense that an oscilloscope is an instrument, and in the way that like a piano is an instrument, right? Because it's sort of precision electronics that's used to create sounds, hopefully pleasant ones for music. And in our case, it's an analog synthesizer. And well, analog is a very emotionally charged word for music people, right? It sort of means like, sort of the protecting the old ways against the new. It's like sort of analog versus digital. What it directly means for us is that all of the signals inside of the synthesizer are in continuous time, as opposed to discrete time. And all of the signal processing that's done inside of this piece of equipment is also done in continuous time. So that's, with the sort of like analog, op-amp, resistor, capacitor type circuits that you saw in 16B. And, other related classes as well. So that's all analog means to us. We can leave the emotional baggage behind, I guess. And the last word here, modular, what that means is that if you were to unscrew the lid off of the Werkstatt, which I encourage you not to do, they're very expensive, but if you did that, you would see that it's not just one big monolithic circuit inside of there. It's actually split into a bunch of discrete components. Oh, thank you. And it's split into a bunch of sort of discrete circuit sections, which in the music world are called modules. And for us, I would say they're more like systems, because what they do is they either generate signals, sort of a priori, or they'll take in a signal and do something to it, and then spit out another signal, which, for us is exactly what a system is. So this synthesizer actually has a lot of signals and systems sort of knowledge and engineering built right into it. So it's sort of a good candidate for us to look at here. And sort of, if you saw the interface of this thing, each one of those little white boxes is sort of like a module. And we'll get into what they all do, because it's not obvious at first if you just look at the front panel of this thing. So I talked a little bit about this just now, but I'll touch more on it now, which is, what does this thing have to do with EE120? I mean, I know this is like a chill lecture, right? None of this is going to be exam material, except for maybe if we give like an extra credit question, but, certainly no hard grades on the material today. But it can't just be a complete non sequitur either, right? It still has to be, whatever we do today should still have to do with signals and systems. And I hope I've convinced you a little bit that that's going to be the case. But there's some other ways as well. Like the main thing that I like about this is that it helps us to get a bit more frequency domain intuition, right? Because, and you might know a little bit about this if you've studied pedagogy or things like that before, but like the best way to gain intuition on these kinds of things, or about a new subject, is to sort of experience it in as many ways as possible. So we've looked at a lot of signals sort of visually, really, like sort of either algebraically in the form of an equation, or also when we sort of plot them and look and see what they kind of look like in the time domain, and sometimes when we plot their spectra too. But the nice thing about signals that are defined over one variable, like over time, for example, is that there's another very easy way to represent them, which is this audio. And, in applications, a lot of the signals are audio, like in a lot of, again, any of this kind of musical hardware or any kind of telecommunication stuff where it's transmitting audio signals, right? Sort of audio is sort of the end goal. So that sort of has a very direct meaning to a lot of engineering applications as well. And it'll help us sort of grok these signals, I think, a little bit better to experience them in more than one way. So I think of this as sort of an educational tool for that reason as well, in addition to just being fun to mess around with. Another thing I wanted to highlight a little bit is sort of the two different ways that you can view these signals. Right? And so I've sort of labeled them here as being the way that engineers think about them and the way that musicians think about them. And maybe that's not a completely fair representation, but I've noticed that there are sort of two camps of people when it comes to these signals. There are people who think of them as being time domain entities first, right, where we define signals in terms of time, and then we take their Fourier transform to get their frequency representation. And it's sort of like the signals are time domain citizens first that have a useful auxiliary representation in frequency domain, but that's just it, a useful representation. And that's the view that I think a lot of engineers tend to have. And this should be contrasted with the way that musicians view signals. And they may not think of them as signals directly, but that's sort of what they are, because they're audio. And maybe you all have some musician friends, or perhaps are musicians yourself, but you know that in that sort of sphere, they're always considered in terms of their frequency domain representation first. Right? So signals are frequency domain entities for them. And the time domain effects are usually never considered at all. I mean, there's no Fourier transforms in music, to my knowledge. And we're going to sort of see how both of those things come out in this hardware demo, because I got this oscilloscope set up, and it's going to show us the time domain and the frequency domain at the same time, because it's like one of those cool digital ones that can do FFT. I think it's really rad. And the last thing here sort of touches again on the first point of multiple ways of learning, but is also going to be a little bit about psychoacoustics as well, because it's actually important, even in an engineering context. But the thing that we have to remember is that we all have a piece of very highly dedicated, sort of high precision, sort of specialized tool for frequency domain processing inside of our heads. It's our ears and our brains, which I think is sort of an underutilized tool for understanding these kind of things. And we'll see that there's actually a lot that our ears can do that a lot of this precision analysis hardware, like oscilloscopes, can't quite reproduce in exactly the same way. And we'll see that our ears and psychoacoustics can do some pretty incredible things. And it's also important to consider psychoacoustics. And what that means, by the way, is just like how audio signals relate to the way that we hear them. That's actually, again, important in engineering applications, because if the final signal in whatever you're designing is meant to be heard by a human ear, you need to consider in your engineering applications how the human ear perceives sound, and that'll affect your design decisions later on. So that's sort of what I want to come out of the next 40 or 50 minutes, basically, is sort of like the high level what I want you to learn. Just kind of keep that in mind. I mean, if you don't want to learn it, that's also fine, because we're not going to test you on it. So now we'll move on to an actual description of the hardware itself. So when y'all saw this thing, and I've been saying this over and over again, it's really not as bad as I'm saying it is, but it's not immediately obvious if you were to plug this thing in and start fiddling with it. It wouldn't be obvious at all what was going to happen, because this thing is there's a lot going on here, and it's interconnected in ways that aren't immediately clear on the surface. So I'm going to tell you all how that works first, and then I'll show you all sort of what it can really do. And it all has to do with the fact that this synthesizer is modular. So there are basically 6 big circuit blocks inside of this synthesizer that are called modules, and those are what are in the boxes here. And these are actually what all define the sounds that come out. Now, you don't have to study and memorize this diagram exactly, but it's just here to get an idea of what's going on. And we can see that I have them sort of laid in vertical and horizontal. And the reason I've done that is that there's sort of 2 distinct kind of signals that go on in here. And so one of them is going to be an audio signal, and it's going to go along that top row. And that top row is basically just an oscillator, a filter, and an amplifier. And those 3 modules, which is a pretty simple, a fairly short sort of system chain, is actually all that produces the sound in this device. So it just goes through 3 stages, and that's all we had to think about for that. But there's these 3 other modules as well, and they produce other signals which you can't hear but are very important for the sound, because they're actually going to modify the way those 3 audio-producing systems, or those audio-producing modules, are going to behave. So we'll look at that in a minute. We'll just do a quick kind of skim through. And I'll kind of go through all these in detail a little bit. So the first one of the audio-producing modules is just the voltage-controlled oscillator, or VCO. In circuits class, have you all looked at oscillators before? I don't think we touched on them in 16B or anything like that. Okay, well, the good thing is we're not going to do a whole lot of circuits today. Basically not at all, except for a little bit of diving through history later on, maybe. But what this block does is it basically produces periodic waveforms, right? It oscillates, and those are going to be the basis of any sound that comes out of the synthesizer. It's going to start in the voltage-controlled oscillator, the VCO here. And, it'll get processed by the other one, so it won't just come out of there, but it starts here. And the way it works is it basically produces one of two different waveforms, right? We have this sort of impulse train kind of square pulse wave looking thing here, and a sawtooth wave as well. And those are going to come out at some frequency. And the frequency itself isn't fixed. That's what's really cool about the voltage-controlled oscillator, is that there's like an auxiliary input, which is basically going to be a voltage, and that voltage decides what frequency this thing is going to oscillate at, right? So we can control that manually as well, but we can also let it be controlled by the other module. So the frequency at which this thing oscillates can actually change over time, and that's going to be an important part of how the sound is generated. But sort of basically, this is what it does. And I guess one of these signals at least should be a familiar friend to us, because we've sort of looked at these pulse-type waves before. So we actually know a little bit about their frequency spectrum from the analysis that we've done. And we'll see that reflected in the hardware as well. That other one, the sawtooth wave, I don't believe we've looked at in this class, but it's not too much of a jump from, kind of like a triangle wave or a pulse wave. But we'll see it behaves a little bit differently in a way that ends up being musically interesting. So that's all that's going on inside of the VCO. So the next part in the audio chain is the voltage-controlled filter. And this is a little bit easier to explain because I think most of you have seen, probably saw like actual analog filters in 16B, and if not, then we've at least talked about them in this class. So you all kind of know what a filter is. And this is actually exactly the same kind of filter that you're all familiar with. In this case, the only real difference, I guess there's two differences, but the main one is that it's a pretty higher order filter, right? So you can see it's a fourth order filter, which means it actually has 4 poles in it, or like, I don't know how we describe it in terms of this class, but like in 16B, for example, we'd say it has like 4 different eigenvalues going down, or 4 different poles, something like that. But what that means is that it's a strong filter. So once you go past, and it's a low-pass filter too. So what that means is that once you go past the cutoff frequency, the value of the transfer function here actually dies down pretty fast. The way you would describe that in terms a musician would understand is 24 dB per octave. So I guess we didn't talk about decibels or dB in 16B, which is a shame, I suppose, but basically it's sort of analogous to the logarithmic scale. So like every 20 dBs basically is going to be an order of magnitude decrease in the strength of the signal. So what that means for this fourth order filter is that every octave, like every time the frequency is doubled, the transfer function is going to go down by an order of magnitude, or like a little bit more, once you get past the cutoff frequency. And we'll see why it has to be so strong later on. Because like I said, this is a strong filter. Fourth order, you wouldn't normally have to deal with that in a lot of applications. Like whenever you're just trying to filter noise out of like a carrier signal or something like that, you would just look at first or second filters, or first and second order filters, like you did in 16B. But the human ear is a special application, and it requires something really strong, and you'll see why. The other thing is that we can also add a neat little resonance peak at the cutoff frequency. So what will actually happen is that the cutoff frequency itself will be strongly magnified, and then everything past it will sort of get cut off. And that'll produce a very interesting sound later on. And the math behind this is pretty weird and complicated. Thankfully, we don't have to deal with it. Oh yeah, so here's the last of the audio producing modules, is the voltage controlled amplifier. In a way, it's kind of the simplest of all of them, because all it actually does is it basically takes the audio signal that just came out of the VCF and some control voltage, and it basically multiplies them together, because it's basically an amplifier with variable gain, and the gain is going to be decided by this control voltage. And what that basically means, effectively, is that you're just going to multiply them together. So it doesn't look too analogous to a lot of the systems that we've seen before, but this is in fact a bona fide system just like any other. As a matter of fact, would you say that this system, like we have the input-output equation here, would you all say this is a linear system? Like imagine what happens if you replace x of t with x of t plus y of t, for example. Or sorry, x1 of t plus x2 of t. Like what would happen in that instance? Like you see, you sort of get the same thing as if you would add the outputs together. So the system is in fact a linear system, which is kind of cool, I think. The thing is that it's not a time invariant system, right? So this control voltage, it's sort of separate of the input you can think of. So shifting around the input time would do funky things, and we might even be able to take a look at that later on. So this is a linear but time varying system. It's also memoryless, because everything just happens directly at time t. But I just think that's cool that we can analyze that one sort of with our tools directly. So that's the last of those modules. And I'll also talk a little bit about the two control voltage modules. So these two which are the envelope generator and the low frequency oscillator, they don't produce any sound, but this is actually where all those control voltages that are going to do funny things to the other modules, this is actually where they come from. So with the envelope generator, this is sort of what will produce sort of the sound, the volume dynamic envelope of the signal itself. You can see that what it actually does is whenever you hit one of the keys on the synthesizer, it'll actually produce one of these sort of mound-shaped signals, and you can control the length of sort of the two sides of this trapezoid here, right, which are called the attack and decay in musical terms, and we'll see why that is. You can sort of control that directly with two knobs that we have on here. And there's not too much going on in the signal, but again, we'll see that this can produce interesting effects. And the other one, or the other control voltage module, is called the LFO, which is short for low frequency oscillator, which is sort of an historical term actually. It actually can go to quite high frequencies, but it's actually a very similar circuit to the voltage controlled oscillator, except you don't hear it, it just sort of modifies things. And it can produce square waves and triangle waves like this basically. And we'll see what kind of effect that has on the sound too. So that's actually all the modules that we care about. There's one additional one that I mentioned, or that was on the diagram, which was the keyboard, but I think that's pretty self-explanatory. Like, you press the keys, and it will modify control voltage as well. Like, it'll go from 0 to 1 based on whether or not you press the lowest or the highest key. And that's about it. So the last thing I want to talk about, and I'll touch on this point later, is that in the original diagram we have here, which I've reproduced, there's a certain set of fixed connections here of how the different control voltages can affect which modules, and which of these audio modules are connected to which ones. This is actually not fixed. Well, those ones are fixed in the sense that you can't get rid of them, but it's not fixed in the sense of that's all you can do. There's actually a little patch of things on the right side where you can add in new connections, basically to any of these modules that you want, and that can produce a lot of other interesting effects as well. And hopefully if we have time, I'll show an example of what effect that can have. All the connections you can make don't necessarily make musical sense, but for the most part, they're at least interesting experiments to try. Alright, so that's about it for the exposition material. So I think we're just about done with that. Let's see, how does this look? I'm switching to the document camera now, because we can actually get to the interesting hardware part now. So here's the other Werkstatt that I was talking about before. I've got it hooked up to two sources. I have it hooked up to the speakers, and I also have it hooked up to channel 1 of this oscilloscope here. That'll do, I guess. So this way you can sort of see what I'm doing on the Werkstatt and also see what's happening to the oscilloscope as well. Here, so I have it set up right now. So what I do, or what'll happen if I press the button now, is it'll just produce roughly a square wave, kind of like this, just like that. And I'm going to turn the audio on now so you can actually hear what this thing sounds like. But I want to make sure I don't blast y'all out as well, because that would be, well, not great, obviously. Hang on a second. Fantastic. Laptop audio only. There we go. Fantastic. So let's take a look at what the voltage controlled oscillator does on its own now. So I have it set up so that the voltage controlled filter and the voltage controlled amplifier aren't really doing anything too interesting. All right, so I have this cutoff knob on the VCF all the way to the right. And what that means is that the cutoff frequency is going to be way high, so it's not going to impinge the sound of the VCO. So we can hear what that sounds like just on its own. A little bit higher. I think that's good. So this is, as you can see, it's actually, what we see on the oscilloscope isn't quite a perfect square wave. Now I've actually looked at this thing sort of on its own without anything else attached to it. And it actually does produce a pretty good square wave. It's not perfect, but it's a little bit better than the one we just saw. But I have some additional connections here in order to make this demo work. So does anyone have an idea of why we're seeing on the oscilloscope something that's not quite the true waveform that the Werkstatt puts out? And you can think about it in terms of 16B, it's where we sort of learned about the effect that RC filters can have on a signal. Yeah, it's sort of like there's some additional stuff happening, and so there's some resistance, and there's actually a bunch of capacitance as well. And the reason for that is that I have this big audio cable. Well, it's a small audio cable, but it's quite long. That's going from the output of the Werkstatt all the way into the audio box for the multimedia system here, and that's going into the front end of an amplifier. And that whole cable amplifier front end actually presents a pretty big capacitance and a resistance to the output of the Werkstatt. So it's like we've taken what we put out of the Werkstatt and put another filter on it, which is unfortunate. There's really no way to get rid of that without, just sort of not being able to hear it, and obviously I don't want that. So we'll just have to keep that in mind. I mean, the signals still come out pretty well, but you can still see that it's pretty square wavy, for example, and it's not too far off from the real thing. So like I said, there's two different waveforms you can get out of this thing. So I have it to the pulse setting. We're getting kind of a nice square wave now, very electronic sounding. Like, some people really love this kind of stuff. And you can also get a saw wave as well. And you can see it looks and sounds quite different. Here, I'm going to switch it on. I'm going to set the VCA to on now, so that it has a... so we're just going to send a control voltage constant 1 to the VCA. And that just means the note's going to stay on, like that. And I want you all to... By the way, can you see the spectrum okay? Alright. I'm going to scooch up a little bit so you can see it as well here. So now we're going to take a look at the two spectra here. So let me explain what's going on in the oscilloscope, although it should be pretty self-explanatory. So you can see that the top, the very bright yellow waveform, this is the time domain view of the signal that's coming from the audio output of our Werkstatt. So you can sort of... it's exactly like the signals in time that we've been looking at in class all semester. And on the bottom, in purple there, is actually its frequency spectrum. So what this oscilloscope is doing is that every time it captures a new voltage trace waveform, it is immediately taking the FFT of what it gets in, because this is a digital oscilloscope, and then it's plotting that underneath. So that's what we're seeing in purple. So we're getting the time domain and the frequency domain representation of the output signal we're capturing at the same time. I think that's pretty cool. And it also sort of helps us to understand, in systems terms, what's going on. Do y'all remember, I believe it was in homework 2, exercise number 2, where you had to show... Let me turn this off. Where you had to show that a signal that satisfied a certain kind of symmetry had all of its even components nulled out. Do y'all remember that exercise? And it had to do with a pulse wave. So that actually, in addition to being a pretty cool, academic exercise, not the funnest to do because it's sort of a lot of integral drudge work, but it actually has an effect that's of musical importance too. And the reason I bring that up is because we can actually see that here. So if I switch to the pulse wave, and I'll try to set this up a little bit. So I'm going to try to have it, or give it the same kind of symmetry roughly. Kind of hard to do exactly. So you can see that this signal exhibits a pretty similar symmetry. It's not quite perfect. Again, I guess due to the filtering that we're doing here. We can see that some of the harmonics in our FFT are a little bit smaller than the other ones. Here, I'll switch it over so you can see that a little bit better. Just like that. So we have a little bit of cancellation of harmonics here. Whereas if we switch to the saw wave, right, we can see that all of the harmonics, the even and the odd, are all equally strong. Yeah, that way they're really close to being canceled out. And you can see that has a pretty strong effect on the way they sound as well, because they're pretty distinct. So musically you might describe this particular waveform, the sawtooth, as being maybe kind of having a buzzy kind of sound to it. Some people think this, not this particular one, but signals like this are kind of a little bit harsh and sort of brash and buzzy, whereas a sound like this is sort of, oh goodness, it's kind of round and smooth in a way. Not with the same kind of smoothness that like a sine wave would have if we were to hear that, but pretty similar. And the reason for that is the presence of these additional harmonics, right? So it's these odd harmonics, or rather it's the even harmonics that this signal has that produces kind of that buzzing sound that we're hearing, as compared to this signal, which is almost exactly the same, except for it doesn't have those even harmonics. So that's the VCO on its own. That's about the most interesting thing you can do with the VCO without any control voltages or any of the other components. Oh, there's one other thing which I didn't say explicitly, which is that there's this PWM knob here, and what that does is it actually changes the width of these little, of the high versus the low. So remember how we studied like a parametric version of this wave, right, where we could say how long we wanted it to be high or how long we wanted it to be low. So this knob here lets us control something analogous to that. And that actually has a pretty strong effect on the sound as well. You can see this sort of allows us to smoothly introduce or remove those harsh-sounding even harmonics. So we have sort of a nice little parametric view of that. And that's why I was like fiddling around with that earlier to try to get it right. That was what that was. Okay, so with that, we'll take a look at what the VCF does as well. So now we're going to take these raw waveforms from the oscillator, and we're going to start filtering them a little bit with our voltage-controlled filter. So as we can see, the cutoff is all the way to the right. So we're going to slowly sweep this down, and we're going to see what happens to the signal when the cutoff frequency of this filter is brought lower and lower. So I'm going to sweep that knob now. There we go. That's a little easier on the ears, isn't it? And also, this is a little bit where that sensitivity of the human ear comes in, which is that between this signal and this signal, they actually don't look all that different when you look at it in the time domain view, but boy, can your ear tell the difference, right? Like there's a world of difference between this sound and this sound. You can see it a little bit better on the spectrum, which makes sense, because that's what your ear is sort of looking at, so to say. But I think that's one interesting thing, which is that your ears can actually kind of beat the oscilloscope in this one kind of way. Here. So now, I actually only have I don't have the filter turned all the way. Actually, just sort of part of the way. And you can see that we've removed just about all of the harmonics from this pulse wave, except for the first couple of ones. And we have something that looks pretty similar to a sine wave. This machine actually can't produce a sine wave on its own. It just doesn't have the right kind of oscillator for it. But it can do a pretty good approximation to it. So I'm going to turn that up a little bit, because it's pretty quiet, mostly. But this is actually what the sine wave on its own kind of sounds like. It's honestly a pretty weird sound. Ooh, goodness. Blow the house down like that. But a fairly pure sound like that. Oh yeah, that's the other thing I didn't say about the VCO, is we can control, in addition to giving it control voltages from the other modules, we can actually just fiddle with the frequency ourselves. Kind of like that. So all I'm doing is... Here, let me get rid of the filter for a second to show you how that works. Because this is also a fun thing to play with. Is we can actually just make the frequency be pretty much any frequency that we want in the human hearing range. Basically by fiddling around with this knob. And you can get some good effects like that when you just fiddle with it with your hand. But once you let the LFO or the envelope generator take over, it can do even more. Alright, but back to the VCF. And let's also switch over to a saw wave as well. Remember, this had a lot more harmonics. Right? So we should expect something interesting to happen with the filtering here as well. And you can see that the filter has a harder time... Let me turn this up a little bit. The filter actually has a harder time getting this one to look like a sine wave. Like you can see, so we're well past, so you can tell that this audio frequency is actually well past the cutoff frequency, because just by changing the frequency, it's already decreasing in magnitude. And you can see that despite that, this signal in its spectrum has a lot more harmonics in it than the square wave did, or the pulse wave rather. Right, you can see this looks a lot like a sine wave at the same frequency, and this one kind of doesn't. And you can interpret that in frequency domain land as being that this second peak, right, sort of the first harmonic after the fundamental, is pretty weak in the pulse wave, but in the sawtooth wave is pretty strong. And you can see the same thing happening in the time domain. Right? Push that over here. That actually does look a lot like a sine wave, but not nearly as much as this does. So there's a visual difference as well, and just in the time domain, just in between those harmonics being there. But I would still argue that the human ear can do a better job of telling that something is different between these two. Because again, they both sound kind of muffled now compared to what they were, because we've sort of done all this filtering action on it. But you can still tell there's a world of difference in the sound. And there's one other thing you can do here, which is play around with this resonance knob. And this is what I was saying before, is this will actually add a peak at the cutoff frequency. So I don't know if you can see this on the scope. Yeah. So what's actually happening is that basically what that peak in the filter does is what that means is it'll take any signal, and if there's even a tiny amount of frequency content at the cutoff frequency, it's going to pick it up and amplify it massively. So that's why we're hearing that sort of higher pitched buzzing sound right now. That's where that's coming from. And you can see that even if we change the frequency here, that buzz stays at the same frequency, because even though we're changing the oscillation frequency, we're not changing the filter's cutoff frequency or that resonance. And that means there's just a teeny weeny bit of frequency content at that frequency, no matter where we are. And we can change that this way by changing the cutoff frequency itself. Y'all ever heard of or have you ever heard any kind of audio of the Tibetan throat singers? I highly recommend you check it out. It's very neat. And they're actually really good at approximating this kind of filter behavior just with their vocal cords. It's really incredible. I recommend checking that out. But I just thought I'd mention that, because that's what it reminds me of sound-wise, is sort of like this throat singing. I wish I could do it, but honestly I can't. Alright, let me get rid of that. Alright, what do I have scheduled next? Oh yeah, actually, I'm going to take a quick detour into circuit land. I said that we wouldn't do much of that, and I promised that we won't do much, but this is actually a circuit that I think y'all can sort of appreciate. Because you looked at filter circuits in some circuits classes, like in 16B, and if you haven't, then they look basically just kind of like this. Right, these are the kind of filters you'd look at there. Yeah, filters aren't for everybody. And this is the kind of what you look at, and you know that this has sort of a first-order low-pass kind of effect, this sort of filter. And the reason I mention this is because what the circuit, the VCF in here, is essentially no different from this, except with a few bells and whistles on top of it. I mean, for one thing, there's more of them, right, because it's fourth order. So there's basically 4 sections of this, and it uses a special trick in order to make it be variable with frequency. Because this is, or variable with voltage rather, because this is not a voltage variable filter. Its cutoff frequency is fixed. The most you can do is maybe make this like a potentiometer or like a variable resistor that you can fiddle with a knob, but there's not a way to make this voltage variable like on its own. And that's actually one of the things that makes these Moog type synthesizers especially famous, actually, is the way that they do this, because it's pretty clever. So I've found the schematic for the synthesizer online. It's 9 pages, and we are not going to look at the whole thing. We're just going to take a brief look at the page which describes the voltage-controlled filter. So I've got that here. Ooh, the white balance, my God. Can I? No, there we go. It's kind of coming in now. So I'm going to zoom in on the portion of interest here. Well, first, let me show you the whole thing. So this whole page is the whole VCF. And there's some other junk going on. There's this whole section is basically for buffering. This is for conditioning the control voltage. We're going to ignore that, and we're just going to look at the bit that's actually the filter. And that's this bit here. So you can see that it's sort of built into 4 different sort of sections here. And each one of these is one of the poles in the 4th order filter. And you can see that it sort of should be roughly analogous to filters that you've seen before. I don't know if it's coming up on the document camera, because it's atrocious. Oh, shit. How do I change that? Can I go back a little bit? Is that better? No, this just zooms in and out. Maybe... Oh, brilliant. So that's what that button does. Great. Oh, the more you know. Of course, I learned this halfway through the demo. But anyways, what I wanted to say is that we have these 4 sections here, and yeah, you can see now there's a capacitor in the middle of each of those. And that is the same capacitor as in this type of filter here. So the thing that's different are these transistors on either side. And I guess you didn't investigate these particular type of transistors, but they're called bipolar junction transistors. So you learned in 16B, or you may have learned if you took it, that you can use transistors as like voltage-controlled switches. So we know there's like some voltage-controlled magic that's going on in here. What you might not have learned was that in addition to having switching behavior, you can actually do a lot more with voltage control with transistors. And in this case, these are actually being used as voltage variable resistors. So what's happening is that there's a bias voltage at this terminal here, and the larger portion of this current through the transistor is being fixed. And that's being fixed at a certain level, and the control voltage is deciding what that current is. And depending on what level that current's at, that's actually deciding what resistance the transistor kind of looks like, roughly. So I've written out what that looks like here, where basically I've taken each of those, like the same filter portion, and taken each transistor and replaced it with a resistor. And we know that these are voltage variable. So if we turn that kind of 90 degrees here a little bit, you can sort of see that this is basically nothing different than 4 of these LC filter sections. And there's some extra resistors on the bottom. And the reason for that is because since this is an audio circuit, it uses what are called balanced signals instead of the one-sided signals that we look at in 16B. You don't really need to know the difference for our purposes here. But what that means is you sort of have to make the circuit have a little bit more mirror symmetry. So that's why there's a resistor on the top as well as the bottom. So you can see that this circuit, like again, which is very famous, this has sort of been the definition of sort of what musicians call the Moog sound since the time of the moon landing. And it's actually not all that complicated. In a way, like once you sort of break it down, like it's simple enough to understand with just a little bit of circuits knowledge. And I'll mention one bit of historical trivia, which is that in Robert Moog's patent from 1969, again from the time of the moon landing, you can see a circuit that's almost exactly the same. Right, so this circuit, which is on our Werkstatt now, is pretty much unchanged after 50 years. They've been using the same kind of, I guess, intellectual property, more or less. But what that means is that this sort of little machine, even though it's pretty new, actually has a pretty old school sound to it. And I think that's very neat. So that's all I wanted to say about the circuits. There'll be no more circuits after this, I promise. All right, back to the sound. So we talked about the VCO and the VCF. So the only last audio stage left just to talk about is the voltage-controlled amplifier. And its behavior is, there's not a whole lot to say about it, really. But we'll go ahead and say what there is to say. So there's one little box here labeled VCA, and it only has one switch, as you can see. It's just on and EG. And that's saying where it gets its control voltage from. So when it's in the on state, like I said, we just sort of send a dummy control voltage that's just sort of a constant 1. And that just means that the amplifier just passes everything through unchanged. Whereas if we switch it to EG, it'll get us control voltage from the envelope generator. So we'll go ahead and add that in now. And what that means is that when I press this key here, something actually kind of non-trivial starts to happen. Which is that this key determines when it's going to turn on and when it's going to turn off. So what's happening is that whenever I press this key, the envelope generator is producing that, like I said, that sort of little mound of control voltage. And the sides of that mound are decided by these two knobs here, which are refocusing a little bit. I don't know if you can see it, but they're labeled attack and decay. Oh, you can actually see it really great. That's good. So if we increase these a little bit, we'll get a slightly different sound profile. Starting to get a little bit crooked. So I'm going to press the key now. So you can see the sound, instead of just being, a very direct jet, it sort of slowly fades in and out now. And that's coming in from, like, when there's like, when the envelope is ramping up, it starts quiet and then it gets loud, and then it stays loud, and then when I let go of the key, it becomes loud and then goes quiet. Like that. And that's sort of there to mimic the sound that, like actual musical instruments make, because no real musical instrument like a trumpet or a piano just produces the constant 1, right? It sort of has like a dynamic profile. And this is meant to just sort of replicate that behavior. And as you can see, we also have this sustain button on. What that means is that as long as I hold it down, it stays at the top of that mound. But if we turn it off, you can get sort of this type of behavior, where it just sort of, it doesn't stay at the top at all. It just sort of goes up and then goes down. So you can get sort of a nice pizzicato type behavior there. I wish I could play an actual song for y'all. I mean, I'm going to be honest, I'm not a musician. But if any of you are actually musicians, then I highly encourage you to come show us what's what on Friday, because that would be fantastic. All right, so now that we've seen what everything kind of does in isolation, or at least the audio parts of this circuit, what they've done in isolation, let's take a look at how we can modify everything with our control voltages. I'll start off, even though we just talked about the envelope generator a little bit, we're going to keep that in our pocket, and I'm going to start talking about what the low-frequency oscillator does. So it might have been like impossible to take your eyes off, but you can see there's this sort of quietly pulsating LED in the corner here. It's really pleasant to look at, I think. But what that actually is doing is it's showing us what the amplitude of the low-frequency oscillator is. So when this LED is bright, that means high control voltage, and when it's quiet, or when it's dark, that means low control voltage. So we are now going to take this control voltage from the low-frequency oscillator, and we're going to pop that into the frequency of the voltage control oscillator. And we're going to see what that does. And so actually all the circuitry is set up for that. This amount key knob here determines how much of an effect the control voltage is going to have. So we'll just turn that up a little bit so it actually does something. Oh, let me turn the sustain back on. Hear that? So before, of course, it was just staying at one frequency. But now you can see it's going up and down. And in the time domain, we're getting like a breathing kind of effect. And in the frequency domain, it's kind of hard to see because it takes a minute to do the FFT. But you can see that the peaks are all kind of moving back and forth a little bit. And so the reason this is happening is because we're sending this this triangle wave voltage into the control voltage for the VCO. And that means the frequency is going to go up and down like a triangle wave. And we can, this sounds kind of not great. It just sort of sounds like a car alarm siren, I guess, if anything. Or maybe like a tornado siren. So obviously not musically useful as it is. But this is very similar to an effect that's almost ubiquitous across musical instruments, which is vibrato. So we can reduce this effect and increase this frequency here. So now I'm increasing the triangle frequency. So now you can see there's just a little bit of a waver in the frequency there, and you can really hear that too, right? And so it's actually considered good musical practice for like opera singers and for flute players, and I think for string players as well, to sort of induce this sort of wavering vibrato type behavior into their instruments. So it's pretty common in music, and for us we sort of get that effect by modulating the VCO with our control voltage from the low frequency oscillator. Also, I'd like to point out that if I turn this off, right, we go back to no vibrato. Turn it on a little bit. Yes, vibrato. Now, take a look at the scope. No vibrato. Yes, vibrato. No vibrato. Yes, vibrato. Can you tell what the difference was? I sure as hell can't. And the reason I say that again is due to the sort of, the processing power inside of our ears and our heads here. What is it? It can actually sort of pick out an effect that is really hard to tell from, our electrical equipment here. So, again, that's sort of props to our own human psychoacoustics, which is that we're really great at telling when frequencies change, right? Potentially even better than this equipment here, at least at audio frequencies. I mean, I guess once you get above 20 kilohertz, then, the oscilloscope starts to win, but, before then it's our turf. Oh yeah, and you can do a little bit more with the LFO and the VCO, because remember, there's one other thing we can change too. There was like a PWM knob for the pulse wave, so I'm going to show you what that does, because I think that has an interesting sound as well. So now I'm going to switch the destination here from frequency to PWM, and I've also switched this back to a pulse wave. And you'll be able to see the effect of this a little bit better. Yeah, you can see that a little bit. So now this wave is kind of jumping around up here. Yeah. This is cool, I think. This is kind of like... Is this like Stranger Things kind of theme? That's what it sounds like to me a little bit. But we get this sort of like phasing difference. And what's happening is that we're sort of wobbling, this PWM back and forth. And you can see it's really jumping around. That's because, and this is sort of an unintended consequence of the VCO circuit, is that changing the PWM also gives it like a little bias voltage as well. And you can't hear this bias voltage because it's more or less DC. It's like at a couple of hertz. But it does show up pretty strongly on the scope here, of course, because it's showing us everything. So that's what's kind of going on there. And you can get some really weird effects too. Let me tell you, this thing can provide hours of fun just by checking that out. Let's see, I think there's one other thing, at least a couple of other things I wanted to do here. Because it's almost, my hour is pretty much up.
Go ahead, I'll set up.
Okay, do you need me to make any room? Also, this is the guy, this is Nicky Lustig. Well, I guess some of you might recognize him. But you know, like prepare yourselves for an even cooler demonstration in about 10 minutes. Who could forget?
There's 1 and 1, 1100.
Yeah, I think we can make it higher than that. Sit in the front row for starters. Wow. Yeah, see, there's the processing power of the human brain. Forget this frequency stuff. All right, so I'm going to do one more kind of cool sound here. Because I actually don't want to play my whole hand, because I want to save some cool patches and sounds for the demo on Friday. Because if I just show you everything now, then you won't come. Well, you still might not come. Again, totally optional. But I recommend that you do, because it's going to be sweet. So we can affect, like right now, we're just routing this LFO to essentially just one thing, the VCO. We can actually send it to multiple places. So you see that we have another VCO kind of slot here for how we modify. Oh. So we can sort of affect the voltage-controlled filter with the LFO as well. And the effect that that'll have is that at this pulsating voltage, the cutoff frequency for this filter is going to go up and down at that same frequency. So let's take a look at what that looks like. So first off, we'll just look at the cutoff frequency in isolation. Let me turn this effect up a little bit. There we go. I'm going to turn this up a little bit. I want to get it so that you can see like a filtered and unfiltered waveform at the same time. So I'm going to turn this up to a really annoying frequency.
That's how old people are, just by playing sounds and other stuff too.
That's true. However, that's not the point of the point of today's lesson. It is not to alienate, so we shall not. Can you hear anything? I can't. I'm kidding. Let me turn this up a little bit. Yeah, well, hell, you can't really see it. But you can tell there's like a section where this is getting strongly filtered and weakly, right? Because you can see we're pulsing from square wave to sine wave, back and forth really fast. And that's what's sort of creating that sort of breathing kind of humming effect. What I like about this example as well is you can really see it in the frequency spectrum too, right? So look at the purple waveform at the bottom here. You can sort of see all of those higher harmonics sort of breathing in and out as the LFO sweeps up and down. Just like that. And you can kind of see it down here too.
It's only analog here?
Not quite. Well, I mean, this is an digital sense too.
The setup for the screen.
Oh,
It's only VGA?
no, there's the other, well, it has all those other ones too, but I think just the VGA directly, as far as I know. Right here, we're using that for the sound right now. Sorry. Get that out your way at least.
Oh, go ahead. I won't be in your way.
Well, I want to make sure. I'm sure they'll be back. So now we'll do both at the same time. I'm going to turn this amount knob back up so that we get some pulse width modulation in there as well. So that sort of changes not only the sound that we get. Turn that way up. So not only the cutoff frequency, but now the harmonic content itself originally is changing as well. And you can see that has sort of a different sound on its own too. Right, so this is sort of a very gentle breathing. And this sort of really amplifies the effect. And again, you can really see it kind of dancing around in the spectrum now. Because now not only are the peaks themselves getting larger and smaller, but they're sort of shifting around and new ones are forming at the same time. Alright. And you can also change the polarity of the control voltage here as well. I guess you can't really hear the difference in this example. But that's sort of the last thing I wanted to show. So you can see that you can get some pretty cool modifying effects by kind of routing this control voltage to all sorts of different modules at the same time. And I think I'll cut the demo off there for today, because I want a little bit of time for our customary short break at around the 1 o'clock hour.
Man, I sure hope it works.
Don't you think it will?
I know, it's too many conversions.
Oh, I see. How many? Ooh, yikes. Yeah, that's why I like having this dinosaur laptop here, because it's got a direct VGA port here, so I never had to worry about that kind of thing. Well, actually, what I did have to worry about was too much of the future, because one time I was in like a conference room that only had HDMI, and I had no idea what to do, because they don't make a converter for that way. Or at least if they did, they didn't have it there. So that's going to be it for today's... Oh, it's going to be, yeah, just touch the laptop like that. I should switch over now. Go ahead and turn this off since we're done with it. So, oh, isn't it? All right. Saved at the last minute. Fantastic. So remember, everybody, that you too can fiddle around with these sweet instruments. We've got 6 of them actually, and they're all going to be in Cori 204 from 2:30 to 5:30 on Friday. So I recommend coming in and checking them out. And you can do other stuff too, right? We didn't do the patch header today. So you can send the control voltages to even more places. You can have them affect each other. So when you press the envelope generator, like the LFO sort of like goes low then high then low. It's like all sorts of cool stuff. What I'm going to do is I'm going to make a Piazza post soon-ish, in which I'll put a sign-up sheet. In which case, if you want to come to the demo on Friday, basically just put your name down for like what time and like which of these you want to work with. Because I want to have groups of about no more than 5. And I actually don't know if the sign-up sheet is necessary because I don't know how much interest there'll be. But just in case. So there should be slots for about 90 students to have 1 hour each. And if there's fewer people that sign up and you want to spend more time, that's also fine too. I mean, if you just want to like chill for 3 hours and play with it, I mean, I would actually probably get bored of it after 3 hours. But if you want to do that, all the more power to you. We are going to make them available for you to do that on Friday. All right. Let me just gather up all of my crap here, and I'll let Mickey have the stand. Oh, and the microphone too. Oh, and while we're still setting up a little bit, this is now beginning our customary 10-minute break. Can't do without it.
It's running out of battery, by the way.
That was it.
Okay, and where's the microphone, you say?
Oh, yeah.
That can be connected. Damn it. Yeah. It's okay. It's just blocking it, so. Okay. Hey, can somebody remember the number 580? Yeah, 580. Will that be okay? Can you remember that? Thank you. Okay, I think I'm on. Am I on? All right, so I'm Mickey Lustig. I've been asked to come here and speak to you, and I agreed because the main reason is that if you look at the downstream of where you want to go, is to take EE 123 next semester. And I'm just here to confirm that that's the case. Because, to be honest, it's at the end of the class, after you went through all the effort, and the work that's associated with it, you go like, oh wow, that was the most rewarding class I've ever had at Cal. Because that's kind of the comments I usually get from students. And they put their, their project stuff on their CVs and things like this when they take 123. And it's not always been this way, but we just put so much effort into the class just to give the experience of really modern digital signal processing, not just necessarily from the theoretical point of view, but also doing this in practice. Okay, so I'm just here to kind of wow you maybe, or encourage you to perhaps consider taking this. Now I have to say, it is required a lot of work, although we reduced it over the years, but the complaints about the work just have increased, so it's kind of interesting. But it's just also because we have a lot more students that are taking this. So a little bit about what I do for a living. I work here. And but the area that I work in is computational MRI, and the idea there is the marriage between this big machine, this big magnet, the physics, and then a computer. Okay, and how you can combine both in order to get more performance. So affect both the way the data is acquired, collected, manipulated, and how then the data is reconstructed. So all jointly together in optimization. So both hardware, firmware, and software of this amazing machine, which is called MRI. Now, MRI has always been computational because, in fact, this is a Fourier transform machine. You don't know that, but it is an analog Fourier transform machine. It computes the 3D Fourier transform of your head. Let's say if you put your head inside a magnet, and then you try to make an image, it actually computes the Fourier transform of your head and then samples along some trajectory in this multidimensional frequency. I don't know if you've talked about Fourier transform. Turns out there's more than one dimensions in Fourier transforms, because if you can take a Fourier transform of an image, which will be then a 2D Fourier transform, it's actually not too hard. It's just you apply it in one direction and you apply another direction. So, if you have a matrix. And also there's a 3D Fourier transform. And so MRI just calculates it for you, like the physics does that. And then when you want to reconstruct, you take in an DFT. It's sometimes it's as simple as that. Sometimes it's a little bit more complex. So this has always been computational, but now it's even more exciting. And so here's kind of examples of Normally you would see MR images. So just so you could, normally you used to probably heads and stuff, but I don't do just heads. We do a lot of pediatric patients scans. This is a knee. This is a cross section through a knee. It's called an axial cross section. This is a sagittal cross section through a knee, and this is a coronal cross section through a pediatric patient, a whole body of a pediatric patient. It's been injected through with contrast agent, and while the patient is breathing, and we want to see how the contrast kind of moves within the body. Normally, you're used to seeing stills, right? But with computational MRI and the way we acquire data, you can actually get those amazing videos. Now, MRI is dominated. It's like the sampling is actually dominated by the Nyquist criteria. Like, it's really hard to achieve a Nyquist sampling. And as it turns out, Nyquist is only, like everybody told you, like, in order to reconstruct, you need Nyquist? You haven't talked about sampling? Well, 16. Who took 16B? From me. Nobody took from me 16B? Yeah, but did you hear about sampling in 16B? Yeah, right. You heard about Nyquist criteria? Yeah, in order to reconstruct? Like, what's the, twice the highest frequency, right? Like, we need to sample. As it turns out, that assumes nothing about your signal. But if you assume something about your signal, like it looks like an image, it's not like random noise, then you could do better than that. And here's just an example where suddenly this images come to life. And when I'm talking about computation here, I'm talking about solving large-scale optimization problems that are with millions and billions of variables. You need to compute Fourier transform 400, 500, 600 times, and you do it iteratively, and those are 3D, so you might want to use GPUs. You might want to use all sorts of fancy reconstruction or optimization algorithms like stochastic gradient descent. You want to use all sorts of things that you'd learn in 127. So all these are related. So this is really magical, but I'm not here to talk about that. This is just for you to take 225E, which is another fantastic class about MRI. MRI is just this amazing image. I mean, I can talk about MRI forever, but that's not what I'm here for, because I want students taking my class next semester. Okay. This is me, just so you can see. It's my brain, it's my heart. That's great. Okay, so now you've seen me from the inside and from the outside. Okay, so when we talk about signal processing in general, what do we even mean? Why, who cares about DSP? I mean, like, everybody wants to do machine learning today. No, I'm serious. I mean, it's really powerful tools, right? Like, you take data and you do stuff to it, and then like decisions comes out, better images come out, other things. So what is really DSP? So let me argue that, when people are doing all sorts of computer vision algorithm, there's tons of signal processing that's happening in there. Everybody puts out their phone when they want to show something related to the department, for example, because everything in the department is in this phone. You know how much signal processing happens here? I mean, I can't even imagine. Look how many sensors this device has. They're all being processed. What about cameras? You know how much signal processing happens in the camera? What about communication? Like, this device has, how many radios? At least four. Let's say Bluetooth. There's Wi-Fi, 2, because there's, 2 different frequencies, 2 different radios. And then there's the phone, right, the LTE, but, there's different frequencies there, so there's probably 4 radios there. I mean, and how much is done? I mean, it's just insane. Okay, so, tons of stuff. And then, of course, the apps, all the sorts of apps that people are doing and implementing. For example, like, taking a video of yourself, and then from the change of the redness of your face, you can actually detect your heart rate. I mean, people come up with all sorts of sophisticated type of application. So, signal processing, let me argue, it's just, you take one signal, either you take one signal and convert it to another. somehow. Okay, so just filtering, generating some control command, compression, just take something and convert it to another. Or doing interpretation. So this is more the machine learning part of the signal processing. Like learn something from those signals. What's going on. Okay, so the interpretation part of it. And then what's cool about DSP, which is discrete time signal processing, is that we're talking about discrete samples. Now, once you have samples, they're represented on a computer. You can represent things on a computer. You can compute stuff. If it's in the analog domain, it's very hard to work with. I mean, you have capacitors, inductors, transistors, all that stuff. And then if your transistors heat up or your capacitors heat up, they change. And so your filters change and all sorts of stuff like that. It doesn't happen. Once you have a number, it's done. Okay, so that's the cool thing. It's like everything is just a number. So it's beautiful. And those numbers can be a representation of a continuous time signal, but can be like inherently discrete. Okay? Like if I just look at the signal, which is the number of people in this class every lecture, I mean, that will fluctuate, and I can filter it out and do all sorts of stuff to it, right? Analysis. Okay, that could be a completely discrete signal, right? Because you don't have a half a person yet. So why do you want to learn this? Because our world is just covered with signals everywhere. Everywhere there's just signals everywhere. And like no matter where you go, you'll have to kind of deal with it unless you're like programming web. But even then when you're programming web, there's probably some, like you'll have to do some audio stuff. I mean, like or compressed. I mean, like there's always going to be something related to signal processing. It's really good to learn that and know explicitly and implicitly what you're doing when you're providing operations. So a lot of people, what makes it actually strong, for example, if you want to do machine learning, which my group does a lot of, by the way, but if you want to do it well, it's really important to know what the type of signals coming in, how to process them, pre-process them such that it comes out, and what are the implicit and explicit operations that you're applying when you're doing all sorts of operations on it. Are you doing optimal filtering? Is this the best? Are you squeezing all the signal to noise ratio or not? I mean, are you wasting? Who knows? So all this stuff is really important when you deal with signals. And it impacts all, multimedia. Everybody watches Netflix. You know how much signal processing has in like video transmission, both on rate control, compression, estimation, filtering. I mean, whoa, it's insane. And communication, so on and so forth. So tons of stuff. And then people make shitload of money from that part also by doing all sorts of processing of the market signals, right? So, now, when we think about DSP, what's cool about DSP? That you have kind of like a system. It doesn't age. Like if I bought like a filter, like an analog filter, and the analog filter over time will degrade. It'll just become worse. Or if I, remember this thing called LPs? They're coming back. LPs, long player, like the record player, analog ones, cassette tape, VHS, all that stuff is all analog, right? Those degraded over time. Like really, like or printed photographs, right? They become yellow over time. So they degrade. I mean, like storage becomes worse, the system becomes worse. I mean, have the pictures that you took, 10 years ago on your digital camera changed through that 10 years? No, it doesn't change. It's the same. Same JPEG compression, same JPEG uncompression. I mean, it's exactly the same. So those systems don't age. It's great. Moreover, you can have some hardware that, it's deprecated now. It's like the software on it is deprecated, but you can replace that and do firmware upgrades for that particular hardware. What is firmware upgrade? It's just software, right? But it's just software that you less see. Just hidden more inside. And you change it, and now your device can do something else. Or like improve stuff. I mean, that's what digital systems allow you to do. It's just amazing. And then you can do this fancy supercomputing stuff that we're doing in the videos for the MRI, for example, you can't do this in analog. It's just not. I mean, there's just no way. I mean, what you have scopes and I don't know what to do. Like draw on the sand. I mean, I don't know what to do there, right? So you have to process a lot of numbers. Just some examples. I mean, let me just see. Audio compression. Audio compression. You can compress audio by a factor of 10 by using all sorts of actually models of the human auditory system. So psychoacoustic models learn how people hear, model that mathematics, and then apply that to eliminate stuff that you don't hear, and then reducing the complexity in the signal and be able to compress it. Okay, so huge deal. You take a 30 megabyte file and then you make it into 3. Pretty awesome, right? Because when you want to store it on a flash drive or something, that's a big deal. Changed the whole industry. So here's how it sounds. So I'm going to show you CD quality and MP3, and then I'm going to show you the difference. That's like the original, whatever it is, CD quality.
I am Sid.
That's MP3. I took those samples right on the computer and subtracted the original from the compressed one, and then amplified by a factor of 10.
I am sitting in the morning at the diner on the corner. I am waiting at the counter for the man to pour the coffee. And
So take the original, subtract that part, which means that you don't hear it, by the way, this part. You can't hear it because it's been masked by the original. So that you can't hear it. Well, some people can. Some people can, but they have dog ears. Anyway, hearing, not ears. But my point is that you just reduce this. You reduce the entropy of the signal, and then now you can compress it more. Huge. All right, it's pretty cool, right? Let me just skip a little bit. Digital camera, tons of stuff going on. Digital camera. And of course, you can also use, by the way, with digital cameras, you don't get red, green, blue. You have like an array of red, green, blue that are not the same pixels. And so you do some sort of fancy interpolation there that takes this red, green, and blue array and makes it into an RGB at every place. Okay, that's one thing. And then, of course, you can compress now in 2D. You can compress actually by a factor of 40 with very little loss of information. So you see the difference? There is a little bit of difference, but it's not. This is 40 compression. This is 60 times compression. Here you start seeing, you see, some artifacts over here. Maybe we can darken a little bit the room. You see the difference? Now you see blocky artifacts a little bit. This is called JPEG artifacts. I can point out those artifacts. The problem is once you see artifacts, you can unsee them. I cannot look at videos anymore on TV. I only see the artifacts. It's true. Like everybody looks at the scene, right? Things are moving, right? That has the most bits, and on the corner, nothing is there, like very little, right? So you can compress it more, so it looks blocky, and you don't notice because you look in the middle, and now I look at the side, and HDR. All your phones implemented this, so it compensates for the dynamic range of the hardware by acquiring a different exposures, and then some will be oversaturated, some will be less saturated, and then overall you can combine them all to something which has a high dynamic range, right? And this is computation along with the hardware, right? Like you change parameters on the hardware, then you add computation. It's beautiful. But let's go back to medical imaging. Tomography, computed tomography, CT. Anybody knows what CT is? Computed tomography? X-ray? Who has not ever had an X-ray? Ever? Really? Oh. Yeah, go for it. Yeah, CT. Yeah, computed tomography. CT, CAT scans. Yeah, so X-ray it's like this method where, can I interfere with this thing over here? Ugh. Okay, X-ray is like this. It's like shadows, right? Like you shine light, and then your body is semi-transparent to X-ray, and so when you go like this, then you see the bones. Okay, so it's a projection scheme. And so it's cool, but you can't see the inside. So now I'm just like, woo, I have 2 fingers here. This is why you should be in class and not in like video, because those online cannot see this. So I'm showing here a V that's being projected, right? And then that's kind of 2 fingers, right? But you don't know now it's 2 fingers, right? Like it looks like 1, right? But if you had more angles, you could, right? Yeah. And so the idea of computed tomography is that you make shadows from all angles, and then you get what's called a sinogram, which is this result. Turns out that it has all the information in order to invert it with a computer, right? So you go from there, and then you reconstruct this back. Okay. So that's how computed tomography works. And if you want to learn about that, take 8123. MRI acquires data in the frequency domain. It's all about Fourier imaging. So sounds like that. This magnetic field changing over time. And then the more data you collect, and you get an image. And this is kind of what the rate that MRI data is being collected. So you can imagine if somebody moves, it's going to mess up things. Okay? And that's why we leverage a lot of stuff. Wait, let me move on. I could show you many, many stuff. But I don't want to show you. I want to show you this. Software-defined radios. And the reason I'm going to show you this because in E123, everybody will get experience with software-defined radios. I didn't even say what they are, but you're going to do cool stuff with them. Okay. And the idea there is that traditional radio, you will have the hardware that receives, and you have all the demodulation. Everything is implemented in hardware. And then, sound comes out, or I don't know, something comes out of it. Like TV, like it moves a beam, electron beam, and then creates pictures, right, and stuff like that. So this is traditional radio. Software-defined radio. So software-defined radio is different. Software-defined radio is that you just had this front end which performed maybe some analog filtering, low pass, band pass type of filtering. Maybe brings it to a lower frequency, maybe, but not even necessarily that. And then you've got like a super fast, high dynamic range analog to digital converter that makes samples at ridiculously fast rates, like 256 megahertz. Okay, something like that. That's a lot, right? So, okay, then you get values. Now it's numbers. You take those numbers, you process them now. And you can implement any system that you want using those numbers, right? I can implement the same analog operation, but just digitally. I can decode video. I can decode music. I can, whatever I want. It's beautiful. I can do Wi-Fi, same hardware. I can do anything. Right? Like, mind-blowing. And you know what's amazing? It's dirty cheap now. The hardware is just like IC, integrated circuit. Silicon. It's just so cheap. It's so cheap. You can have like these amazing systems that do like in a single chip that does so much, and then like you just get samples, and then you can implement like amazing systems. Yeah. That's a good point. Yeah, like you can implement an AM radio receiver without needing any power. Like you just need a diode, you need a coil, and you need like a earphone. And then you like connect them, and like you can listen to radio, right? So yeah, of course there's definitely trade-offs. But it's actually not too bad. Most IC today is also low power, so everything is aimed for mobile, right? So it's changing quite a bit. It's just amazing. Okay, so then you've got this flexibility. You can upgrade stuff, sophisticated processing, You can do like the best processing chain, no compromises, and so on and so forth. And cell phones, Wi-Fi, GPS all use software radios right now in it, inside. You just don't know that. But it's probably implemented, in IC. Like the processing, digital signal processing is implemented in IC also, in integrated circuits. A lot of stuff, by the way, implemented in FPGA. So if you take an FPGA class, like there's one on digital signal processing with FPGA, Bora Nikolic sometimes teaches. Really highly recommend. I want to show you just one device. This particular device is an inexpensive TV dongle that costs between 10 to 20 bucks. It's designed originally to watch TV in Europe. Right? It knows how to demodulate and display TV that is the format in Europe. It's not the same as in the US. Okay? So it has a few things. This is a little bit older picture. Now there's slightly different, but RF goes in here, and then it goes into this chip that is a tuner. There's some low-pass filtering, bandpass filtering, and it does some demodulation. It moves, from some frequency to some other frequency. Okay, that's what it does. Okay, that's all in analog. Really cool chip, by the way. And then this chip, the Realtek RTL2832U, has an ADC, analog to digital converter, very fast. It samples those, and then it takes those measurements and then has inside in the IC decoding for all this TV stuff. And then it implements also USB protocol, and then the pictures of the TV goes to the USB. Okay? That's the original. Now, those folks says, maybe some people also want to listen to FM radio. Right? If you want to listen to FM radio using the same chip, we could implement this in hardware. Well, it's kind of hard. It's kind of like annoying. Let's not implement it in hardware. Let's just pass the ADC information, the digital information, let's pass it through the USB, and let's have the driver in the computer do the demodulation and play you FM radio. Nobody knew about this till somebody tried to write a Linux driver for this and then figured out, oh wait, they're putting the samples out. If you put the samples out, that's a software-defined radio for you. You can tune to a particular frequency. You can sample, get the samples. Now you can do whatever you want. And that happened about 8 years ago, and it's really changed all this stuff. And we've been using this in EE123 since then. And it's just an amazing device. So it's really cool. If you think of like classes that relate to this class, there's just tons of them. There's all the classes that you can take that relate to each part of this chain. That part over here is, where's the E120? Over here and over here. E120, 123. And you got all the application stuff too, if you really want to. Okay. So what we do in E123 is you get this device and you get a Python interface to this. You can get samples, and you can do all sorts of crazy stuff, like listen to airplane transmitting beacons, where their position is, decode those positions, and then put it on a map. Okay, so just listen to airplanes. It was designed to watch TV, right? It was designed to watch TV. You know what else you could do? You could do what we do also is we tune into an FM station, and then we decode the FM station in software and play the music. But turns out there's some FM stations that'll have hidden carriers. It's called subcarriers, where they play like music, like elevator music, or other station like Punjabi radio, also some Haitian radio station. 94.1 has those subcarriers. It's hidden. Like you need a special radio that knows how to do that. Well, with this radio you could, because it's all software. So we do that. Like we decode those stations. So it's pretty cool. And then we do other stuff too. And we do other stuff with this device called Raspberry Pi. Do you know Raspberry Pi? And everybody gets an amateur radio license, so it can transmit. And this is a walkie-talkie. Do you know what a walkie-talkie is? Yeah. You walk and talk. But the walkie-talkie has a microphone and speaker here. So we connect those microphone and speaker to the Raspberry Pi and have the Raspberry Pi generate audio signals which actually reflect digital information, and then send data from one Raspberry Pi to another using those. Right? Because voice can be information too. Right? So you implement a modem effectively. And it turns out because this is related to amateur radio, and amateur radios have built whole systems as well. So we were implementing a particular protocol. It's called APRS, Automatic Positioning and Reporting System, that leverage these. These have about 5 to 35 miles range, and you can transmit the messages picked up by what's called nodes, internet nodes, that amateur radio operators they put on their houses, and they get picked up and then routed through the internet, and so you can actually send text messages from the Raspberry Pi without being connected to the internet through this radio. Yeah, no, it shows on your phone. It's crazy. And then we also aimed at the ISS, International Space Station. It has a repeater like that and can relay messages back to Earth. And so you can relay, we tweet it, through the ISS. So cool stuff that you could do. I'll just show you some demos. So there's a lot of badassness that you could do with all those software-defined radio stuff. So I just want to show you some demos. You want to see something really cool? Okay, so this is software, open source software that's developed by people. It's called GQRX, and basically it takes the samples out of this RTL SDR, this thing. This is the dongle, by the way, and it takes samples from there and then demodulates them. Shows the spectrum. So spectrogram. You know what spectrogramming is? It's the spectrum as a function of time, and it shows an intensity. So this is spectrum, and then the spectrum as a function of time. Let me just play it. You hear it? You want to see something really cool? This is a radio. This is a radio. Right? And you know what frequency it's transmitting? It is transmitting at 580 megahertz, 0.5. And my computer now is demodulating that, and I can use now this as a receiver. It's a little bit, it's too strong. So there's feedback. But now everybody could have this device, and now they can hear me directly. You don't have to hear through the like if you had that kind of thing, right? That's pretty cool, right? And the reason I took the antenna off because it's so close that it will just saturate it. And that's where you see the reality of having real signals, because now the ADC is being saturated completely, and so it generates nonlinear behavior, which often you don't even assume. But now I go away. Oh, yeah. Look at that. Can you see it? So I'm talking, and you see that's frequency modulated because the frequency changes over time. So if I speak very weakly, or if I speak more, then you get more bandwidth, and so forth. This is FM, frequency modulation. That's the spectrum of FM, and this is how it changes over time. But yeah, it's pretty cool, right? Anybody else has another radio in their pocket? You do? Anybody has car keys? No, nobody has cars. Undergrads? Yeah, don't have cars. Yeah, you have a remote? Oh, you hold it there. Well, let me just switch the frequency here. I'm going to guess it's 315. because all cars are 315. Do you hear that? You hear that? I can now receive the code that she's sending. It just changes between, intensity, and then that's why you hear the frequencies. Right? Like you can actually, if you actually decode the audio of that, you would see a binary signal. You would see it. And then you can decode the code. Fortunately, there's a rolling code. Like it changes and it's based on something. But guess what? I record this. I'm going to run out to her car. And I'm going to play this. It's going to open it. Because the car, that's the next code, right? Yeah, that's expecting. So the car remembers, I think, like 256 or something codes, like in the future. So if you press on this too much, it's not good for you. Because it will lose synchronization at some point. I think like 1,000 times or something if you press it. So you can actually design attacks based on this, right? That you can listen and do all sorts of crazy stuff with this device, right? What about sources of interference in the room? I can go with an antenna with this kind of device and try to kind of figure out, I got this interference here. I can do tons of stuff. It's pretty amazing. What else? I want to show you. Show you more? Yeah. Have you heard about HD radio? HD radio, as it turns out, there is such a thing as HD radio. So I can go to the FM channels. So radio FM. All right, this is regular FM, 99.7. But I'm going to look for a different frequency. The problem is that we're a little bit in a room. Okay, yeah. There's NPR. You ever listen to NPR? Well, that's great, but you know what? You know these blocks on both sides? That's digital information, actually. It's called HD radio. And only radios that can support HD radio can listen to it. Okay? So the problem is that this is a proprietary protocol, and so you really have to buy them. Guess what? Somebody figured out the protocol. And you don't have to buy them anymore, because I can just go. I don't know if it's going to work. Demos never work, right? Why I don't have it? Hold on. Yeah. Okay. There's a program called NRSC5, which I'm going to run now. NRSC5 And then I'm just going to type the frequency, which is 88.500, 1, 2, 3. And of course I need probably something else. Usage, let's see, frequency, program, 0 maybe? Oh, I need to close this. Hold on. Sorry about that. Close it.
Chunk of music that sounds almost improvised. The song signals to us that this is not going to be the sort of...
This is listening now to the digital version of NPR.
Alabama Shakes made.
Super nice, high quality.
I don't want to do it again.
Like there's no, it's either breaks or works. Like if I remove the antenna, it's not gonna do like,
This album.
it's just gonna like not work because it doesn't get the bits. When I connect the antenna, it's just gonna work. Right? So that's the beauty about that. So yeah, but just with software now, I can do it. Now you can put that on your Raspberry Pi. You can put that on your Raspberry Pi. Now you got yourself, you can maybe write a nice Python program that will just go and have HD radio. Right? It's pretty cool. Oh, talking about the Raspberry Pi. So this is all receiver, right? This is all receiver stuff. Raspberry, so like, you don't transmit anything. It's just receiving. Quick question. Yeah. Complex analysis? I know, 120 is fine. Yeah, 120 is fine. Should be okay. Square wave has a frequency? Yeah? A square wave. Cool. What's the Fourier series of a square? Like something as periodic, right? Square wave is periodic signal, so it has a Fourier series. And you can compute it, right? So it has like harmonics, right? Because it's square. Otherwise, it would be a sinusoid, and it will be just one sinusoid. But it needs to have like an infinite number of, harmonics, right? And it's great, right? So it has this harmonic stuff. It has frequency. So what if I take something that generates a square wave, and I connect it to an amplifier, and then connect it to an antenna? I'll transmit. And what if I only filter the fundamental frequency? So what would happen to the harmonics? Will go away, right? They'll not be transmitted if I filter them before. So in some way, it's kind of like even if I have a square wave, I can generate a sinusoid very easily just by filtering the harmonics, right? Train of thoughts. Okay. What in a device generates a square wave? A clock. A clock generates a square wave. That's interesting. Well, it turns out Raspberry Pi has these GPIO, general purpose I/O, that one of them, one pin, generates a clock, so you can clock some other devices. It's actually a software programmable clock. So people have thought, I can change the frequency of that clock. How about I change it at a certain rate that it actually does frequency modulation? Okay? So, you take a Raspberry Pi, you connect to this pin a wire. Okay? Now, if all of you would look at your phone, you can see that there is actually a new network here in this area. It's called EE123 network. And I'm just going to show you a demo. It's going to modulate at 434 megahertz. Okay? And I'm now connected by Wi-Fi to the Raspberry Pi. And I'm just going to run this demo. this radio is listening to 433 megahertz, okay? And I'm just going to choose one of those demos. Let's see, one of them is narrow band FM, because this is a FM radio, narrow band FM. I'm going to choose this one, okay? And I'm just going to press on enter here.
Dedicated to the proposition that all men are created equal. Now we are engaged in a great civil war, testing whether that nation or any nation so conceived.
The Raspberry Pi is transmitting FM. That's being decoded by this. Oh, I have a good idea. I have a great idea. Let's pick a different frequency. Ooh. 580.5, what was it? 580.5. And then there is also here, I think, broadcast modulation with RDS. Yeah, that would be the right one. Now it's transmitting. Was able to transmit with this, and as it turns out, people actually made many systems on this that can transmit, in the amateur radio frequencies, signals at frequencies that can actually propagate through the ionosphere and be reflected by the ionosphere, and propagate to other places on Earth. Protocols that are low bit rate, lots of error correcting codes. And that people have developed with stations that monitor them all the time. Amateurs do that. And you can actually, from directly connecting the Raspberry Pi to an antenna, I transmitted a signal that was picked up in New Zealand. This is 0.1 watts. 0.1 watts. And that was picked up 10,000 kilometers from here. Crazy, right? Well, that's signal processing for you, because it's not only just the radio and its generation of this, but it's also the sophisticated mode of communication that allows you to communicate, error correct, detect, and recover signal at heavy low SNR. Okay, this is pretty amazing stuff you could do and learn a little bit about them. Some things you learn more, some things you learn less. But I actually made another demo. Do you have my crank radio? I don't know if it's going to work, but let me just try this, because there might be too much interference here. The idea here is the following. It's based on this paper. Who's taking 61C? Raise your hand. Renell? Oh, no way. Because I'm going to do this demo in 61C as well, because it's related. Turns out you can put instructions that go to the memory, right? And the memory is connected to the bus. The bus is a long piece of wire, okay? And if you access that bus, then pretty much it turns the voltage on that bus high and then low, and based on the bits that you're sending to the memory. And you can do a loop, and you can repeat sending to the bus, same bits, and it's high, low, 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 high, low. Sounds like something? Sounds like a square wave. And you can make the bus on the computer transmit radio over the AM band. Crazy, right? It actually leaks information. You can have information transmitted by leaking radio from the computer and play Mary Had a Little Lamb or something like that, or Morse code, or all sorts of stuff. I don't know if it worked last night when I did it, but I don't know if it's going to work. I think it's this one. So what I'm going to do now is I'm going to run some code. Nope. Is it here? No, it's here. Thanks. I'm going to run some code here